Um, in this part of reaction kinetics, we are going to talk about reaction mechanisms. We start with a definition of reaction mechanisms. So usually you are given reactions which I call an overall chemical reaction, like the chemical reaction that we have here. Usually you are given reactions like these. In actual sense, most of the reactions do not happen or do not occur like shown by this overall chemical reaction. Most reactions occur through several steps. These steps, we call them elementary steps. So reactions actually occur through several steps. For example, this reaction, this overall chemical reaction, occurs through two steps. In step 1, hydrogen reacts with ICl to give hydroiodic acid and hydrogen reacts with ICl gas to give hydrogen iodide gas and hydrogen chloride gas. So that's step 1. The second step, hydrogen iodide reacts with ICl. This should be gas, not solid. So hydrogen iodide reacts with ICl gas to give hydrogen chloride gas and iodine gas. That is the second step. Now, when you add the two steps, they will give you this overall chemical reaction. So really, when we think about chemical reactions, think about the elementary steps. All the steps that are involved in that chemical reactions are known as elementary steps. So this reaction is elementary step 1. This reaction is elementary step 2. The overall chemical reaction is when all the elementary steps are added to give a resultant reaction or a net reaction. So that is the overall chemical reaction. A chemical reaction we get after adding all the elementary steps. Another definition is reaction intermediates. Reaction intermediates are species that are not present in the overall chemical equation. For example, in this case, HI, you see here HI in this elementary step, and we also have HI in this elementary step, but we don't have HI in this overall chemical reaction. So HI is an intermediate because it is present in the elementary step but not present in the overall chemical reaction. Now let's see if we can solve one or two problems. But first, let me define what we call molecularity. So for a chemical reaction, molecularity is the number of reactant species in each elementary reaction. So the number of reactant species, not products, but the number of reactant species in each elementary reaction. For example, this one has a single species, A, to give products. it is called unimolecular because there is only one reactant species. This one is called bimolecular because it has two reactant species. So 2 is bimolecular. This one also has two reactant species, also bimolecular. But you can see here, these are two similar species. So we can write them as 2A to give you something. So 2A is also a bimolecular because we have two similar species. While here, you cannot write these as 2A. They are A plus B. But we have two similar species. Termolecular, we have three types. Where we have 3A, that is A plus A plus A. And then we have 2A plus B, that is A plus A plus B. And then we have A plus B plus C. Since we have three species, we call them termolecular species. So these are just examples. This is an example of unimolecular, an example of bimolecular, having two of the same species, an example of bimolecular having two different species. Termolecular reactions are rare, but they are available, but they are rare, so we are not going to talk much about them. So think about how we give the rate of reaction for these equations. So this is rate of reaction for a unimolecular, this one for bimolecular, this one for bimolecular but with different species. Termolecular, one species, termolecular with two species, termolecular with three species. That's how we give the rate law of these reactions. Now, how do we solve problems based on reaction mechanisms? So really, as we said earlier on, reaction mechanisms will give you all the steps that your reaction will take. So let's look at this example. Determine the rate law of the overall chemical reaction based on the given elementary steps. So here we have elementary step 1 as your E step 1, that's elementary step 1. This one is elementary step 2. So let us take note of these two steps. We have a slow step, which is this one, and we have a fast step, which is that one. So the question is, what is the rate law of this reaction? First, rate laws are given from the concentration of reactants. So that is one important thing. So rate laws are given from or using the concentration of reactants. That is the first thing. The second thing, the rate of a chemical reaction depends on the slowest reaction. So rate of chemical reactions depends on the slowest elementary step. So from our question we have two steps. Let me call this one step 1, this one step 2. So you are given only 2 steps. Each step has its own rate constant. Step 1 has rate constant K1, step 2 has rate constant K2. But what are we saying? We say that rate laws are given from concentration of reactants. So you can use the concentration here to give you the rate law, or you can use the concentration here to give you the rate law. But the second statement says rate of chemical reaction rate of chemical reactions depend on the slowest elementary step. So this one has the slowest elementary step, which means our rate will come from this reaction. This one will not give us our rate because its elementary step here is fast. Therefore, I will say for this reaction, rate is given by K1 NO2 Cl, because this is the rate law of the slowest elementary step. So the question was, determine the rate law of the overall chemical reaction based on the given elementary steps. So eventually we'll just say rate is equal to K NO2 Cl. Why are we saying that? Because we know rate law is given from the concentration of reactants. So this one is the reactant here. NO2 Cl is the reactant. The second statement says rate of chemical reactions depend on the slowest elementary step. So step 1 is the slowest elementary step. Another thing that we talk about is construct a reaction profile of this reaction. So we need to take note that we have 2 steps. So we have step 1. Step 1 had NO2 Cl gas with K1 to give NO2, also gas plus Cl. So we say this is a slow step. Step 2, we had NO2 Cl also gas, plus Cl to give, that is K2, to give NO2 plus Cl2. But this one is fast. So what does the reaction profile show? A reaction profile just shows the progress of the reaction. So reaction profile shows the progress of a chemical reaction. Now, this reaction has two steps. The reaction profile must show all the elementary steps. So reaction profile must show all the elementary steps. And usually the height will tell you which reaction is fast. So if we want to draw a reaction profile, we'll have the energy side, and then this part is reaction progress. This reaction is, I'll just say, this reaction overall is exothermic. So if you want to draw a reaction profile for this reaction, we need to take note that it is exothermic. So I will start here. I will start with the first step. The first step captures this reaction here, and we know it is slow. So for the first step, it will have a big bump because it's a slow reaction. So that is step one. The second step is a fast reaction. So it will have a smaller bump. That is step 2. So this one is slow step with a huge bump. This one is a fast step. In this case, this step is reaction 1, this step is reaction 2. So what we are saying is when you have two peaks, this means two elementary steps. So the slow reaction has a bigger peak. The fast reaction has a smaller peak. So for this chemical reaction to really move, it should depend on this big peak. If the reaction is able to climb all the way here, it means it can easily also climb here. That's why the rate of reaction or the rate law of this reaction depends on this big peak. That is the slowest. of this reaction. So 2 steps, 2 peaks. This side we have energy, this side we have reaction progress. Let's look at another problem. As we already said, among the elementary steps, the slowest reaction will determine the rate of the reaction. So our rate law will depend on the slowest reaction. Now here we have 3 elementary steps in this reaction. We have a fast one, but this is fast equilibrium. So it goes in front, it goes backward. We have slow, we call it rate limiting. Rate limiting because rate will depend on this step. So the reaction rate will depend on the second step. And then we have the third step that is just fast, but it's not equilibrium. So we have step 1, we have step 2 here, we have step 3. So immediately we know that this reaction is going to have the reaction profile for this reaction is going to have 3 peaks. So the first peak for reaction 1, the second peak for elementary reaction 2, and the third peak for elementary reaction 3. So let us just start with the peaks. So this reaction is also exothermic. So I'll have my first small peak and the second larger peak and the third small peak. So 3 peaks means 3 elementary steps. That's what it means. And this one is the slowest step, is the one that has the highest or the biggest peak. So I'll keep this reaction profile here. This side is energy always, and this side is reaction profile or reaction progress. So if I ask you to draw a reaction profile, make sure that you have everything that I need in a reaction profile. So I'll say this one is a reaction profile. Now, we want to determine the rate law for this reaction. So I'll just put the reaction again that we are determining the rate law from. So this one is 2NO, forward, backward. Because it's an equilibrium, the forward is given K1, the backward is given K minus 1 as its rate constant. So I'll get rid of these gases. This reaction is in gaseous form, so just take note of that. So this is 1. The second step is H2. plus N2O2. Now the second step is given the rate constant K2 to give water and N2O. So this is step 2. Step 3 is given by N2O plus hydrogen to give N2 plus H2O. So this is 3. When you add all those, you get overall chemical reaction H2 plus NO 2H2O plus N2. So this one is overall chemical reaction. And we know that this one is fast but equilibrium. This is slow. This is also fast. So fast equilibrium. Now, how do we solve a problem like this one? First, we need to know that the slowest reaction will give us our rate law. So that's the first thing. So rate law will depend on the slowest reaction. In this case, our slowest reaction is number 2. So we'll say that rate of this reaction is given by K2, the concentration of reactants. So that's what this rate should be, because elementary step 2 is the slowest elementary step. So that is our rate of reaction. The problem we have with this reaction is the problem of the rate law is the presence of N2O2. N2O2 is an elementary step. So elementary species must not be found, not elementary. N2O2 is an intermediate. So intermediates must not be found in a chemical, in a rate law. So intermediates for example, in this case, N2O2 are not included in a rate law expression. So do not include intermediate in a rate law expression. So how do we get rid of this intermediate? Why is N2O2 an intermediate? Because it is not found in the overall chemical reaction. That's why it is an intermediate. Now we need to find a way to get rid of N2O2. So always, when you see that your slowest step has an intermediate, most of the time or always you will be given an equilibrium reaction that will get rid of that intermediate. So in this case, what is our equilibrium reaction? Reaction 1 is an equilibrium reaction. So let me write it down here. 2NO, equilibrium, K1, K -1 to give us N2O2. So this is an equilibrium reaction. How do we use this reaction? What we are going to do, we are going to replace N2O2 by NO. How do we do that? For this reaction, forward reaction, is equal to reverse reaction. So in terms of speed, the forward reaction is equal to the reverse reaction. So what it means is the rate of the forward reaction, which is given by K1 NO squared, is equal to the rate of the backward reaction, which is given by K minus 1 N2O2. So these two rates are equal but opposite. So this means this concentration N2O2 is equal to K1 K minus 1 NO squared, which means everywhere there is the concentration of N2O2, we can put NO squared, K1 K minus 1. So let me write this again, the next page. We are saying N2O2 is equal to K1 K minus 1 NO squared. But our rate law we found for this reaction was rate is equal to K2, that is from the slowest step, H2 and N2O2. But we are saying instead of N2O2, we should put this one. So based on this, we can say that rate is given by K2, H2, then the whole thing, K1, K minus 1, this thing here, NO squared. So what you do is we can take this one, K2, K1 divided by K minus 1, H2, NO squared to be our rate. So the whole thing here can just become one rate constant, because a constant divided by a constant will give you a constant. So this just becomes K H2 NO squared. Now, that is the rate law of this reaction. Why did we why did we do the equilibrium thing? We did the equilibrium thing because we didn't want this intermediate to be in our chemical reaction. So we had to replace it with something that is in the overall chemical reaction. And how do you do that? You need to go to look to the equilibrium. Because if there is equilibrium, then you can easily remove a species that is an intermediate and replace it with a species that is in the overall chemical reaction. So if I can go back to write the overall chemical reaction. Our overall chemical reaction is 2H2 gas plus 2NO to give us 2H2O gas plus N2 gas. Our rate rho is K H2 then NO squared. And you need to take note that the rate of reaction does not depend on stoichiometry. It does not depend on this coefficient at all. You can see here there is 2, but here there is 1. Here there is 2, here there is 2. It's just a coincidence. So the overall reaction equation does not depend on the coefficient, or rate of reaction does not depend on the coefficient of the overall chemical reaction, but it depends on the coefficients of elementary reactions. So study these chemical reaction mechanisms so that you can use them when we solve these problems in class. Thank you.